All right, guys, so here's your lesson for the day. If you would like to try these warm-up problems real quick, pause it and try them before I go through them, but I'm about to go through them. So we've looked at square roots in the past. The square root of 9 would be 3. Technically, yes, it could also be negative 3. If we were solving an equation, we would definitely consider the negative version. Some standardized tests and things will only be looking for what they call the principal square root, which is the positive root. Some of them, like number 2, will give you that they want the negative square root of 121, which would be negative 11. But sometimes when we're solving an equation, like number 4 down here, when we take the square root on both sides to solve the equation, we have to remember that it could be a positive or negative 7 because we need to know that x could be either one. The reason for putting the plus or minus is not just because it is positive or negative square root, but because we have to consider the fact that it could be a positive or negative root when we don't know what x is. So, number 3 here, square root of 25 squared. Remember, think about what squaring a square root does, or you can even think about it as the square root of 25 is 5. 5 squared is 25. Either way, the square is the inverse of a square root, and so it, for lack of a better term, it undoes the square root. I know that's not a proper English term there. So we dealt with square roots a lot in that chapter on quadratics. If you can't tell, roots are going to be a key in this next chapter as well. So also in the quadratics chapter, we ran into some equations that looked like this, where you had x minus 1 squared. We did these when we were doing the completing the square format. You can still take the square root of that and end up with x minus 1 is equal to plus or minus 8, the square root of 8. Then we add 1. When we add 1, we get 1 plus or minus the square root, 1 plus or minus 8, sorry. 1 plus 8 is 9. 1 minus 8 is negative 7. Because either one of these, if you plug in negative 7 here, it would give me negative 8 squared, which is 64. Or if you plug in 9, 9 minus 1 would give me 8 squared, which is also 64. So in the quadratics chapter, we focused on using square roots to help us solve quadratics that looked simple like these guys here, or we made them look like this when we did the completing the square format. And so what we're looking at in this chapter is extending this concept further. And what I mean by that is you can take the concept of a square root and extend it into other types of roots. So, for instance, and you don't need to copy this down, 2 is the cube root of 8 because 2 cubed is equal to 8. So we've looked at the square root of 4 before, and we realized that it's 2. But 2 is also the cube root of 8 because 2 cubed is equal to 8. 3 is the 4th root of 81, since 3 to the 4th power gives me 81. So what we have to do here is we have to kind of combine some of our knowledge of how exponents work, as well as understanding that some perfect cubes or perfect 4th powers also have roots to them. And the way that we write that root is we use a little index, which gives the degree of the root. The little index number is a little number that you put on the outside of the radical on the little bar of the radical. The number that is on the inside of the radical has a name. It's called the radicand. I'm not going to test you on that because it can get a little confusing there between those, but it is nice for you to know. The key thing that you need to understand is that this new index number that Mr. Harrison is talking about is what gives us a new type of root. It asks us to find a different type of root other than a square root. That's why Mr. Harrison made a little bit of a big deal about you understanding that a radical is what this symbol is called. It's not called a square root. And I know a lot of us, have grown up with that being the only thing that we were focusing on is square roots. But now that we're in Algebra 2, we're kind of stepping up our game a little bit. We're heading up towards the point where now we're talking about roots that are cube roots, or fourth roots, or fifth roots, or sixth roots, or eighth roots, depending on what degree number is here on the outside. That's why you'll hear of this concept called an nth root. And the concept is this: if you have something raised to a power, for instance, if you had 3 to the third power, that would give me 27. Well, that means that if you took the cube root or the third root of 27, the answer would be 3, because a cube root is asking you what times itself 3 times, or what to the third power gives me 27. If you look at this a different way, 27 is 3 cubed, so the cube root of 3 cubed will undo the cube, and so it gives me 3. You do need to understand this concept right here in this little table that's at the bottom here. If you want to pause the video and copy it, that would be probably a good idea. But basically what it says is that if you have nth roots, when you have an even degree root, then you are going to end up with 2 answers if the number on the inside is positive. And so you might want to make a little note right here. We're talking about the number on the inside here. If the number on the inside is 0, then you'll have 1 answer. The square root of 0 is 0. The cube root of 0 is 0. The fourth root of 0 is 0. So you only have 1 answer. But if you have a negative number on the inside of an even root, you're not going to have any real answers. Remember, this is where our imaginary roots came from with square roots. The good news is with cube roots and fourth roots and fifth roots and sixth roots is I'm not going to ask you to find the imaginary numbers for those. Here's where it gets a little different. When you have an odd root, like a cube root or a fifth root or a seventh root or a ninth root, remember you're asking yourself what times itself that many times gives me the number on the inside. And if you have that, if you have a negative number on the inside, you can actually get an answer. We're going to do that here in just a little bit, so I'm going to come back to that in just a second. But it only has 1 answer when you have an odd root. There is not going to be 2 answers. There's not going to be a plus or minus when you're dealing with an odd numbered root. So the little index number gives you what degree the root is. It asks you what times itself that many times gives me the number on the inside. And we'll also deal with some variables here in a little bit probably. Maybe not this video, maybe when we get into class on Monday. But I'll see. I might try to get to some of those before the end of the video. So an nth root is finding a different root than a square root, like a cube root or a fourth root or a fifth root. The key thing, like I said, is understanding what it's asking. So we've already done this one, and I apologize for jumping ahead of myself there a little bit. But let's look at the others down here. And I'm going to cover these up so you don't try to jump ahead of me too much here. This is the fifth root of 32. The fifth root of 32 is asking me what times itself 5 times. Or another way to think about it is what to the 5th power gives me 32. Think about it for just a second. So the answer would end up being 2. Because 2 times 2 times 2 times 2 times 2 is 32. 2 to the 5th power is 32. So the 5th root of 32 would be 2. This is where it gets interesting, and this is what I was talking about. If you have an odd root like a cube root or a 5th root or a 7th root, notice that this one right up here that we just did, you could not tell me that -2 would work, because -2 would not give me 32. It would give me -32 if I multiplied it by itself 5 times. And so that's where you have to be careful with odd roots, is there's not actually an imaginary answer to odd roots. You would actually have to find the cube root of something like -216 by thinking what times itself 3 times, or what to the third power gives me negative 216? The answer would be negative 6. So negative 6 times negative 6 times negative 6 is negative 216. You can double check your answers that way. You can also say negative 6 raised to the third power would give me negative 216. So these higher degrees of roots, what we are doing is we are finding this little index number is telling me what I'm looking for as far as an exponent or times itself that many times. Just like a square root, like we did earlier, like the square root of 9 is 3 because the 3 times 3 gives me 9, or 3 squared gives me 9. It's asking me for a square root. Now, some of you are probably going to start making the, not really mistake, but you'll put a little 2 right here when you're thinking about square roots, and that's fine. It's not wrong. It's just not needed. So, when we are looking at these higher degrees of roots, your brain has just got to adjust to a higher exponent or a higher number of times that you're multiplying something. You need to understand that concept. You need to also notice, like right here, the square root of 9 is 3. The cube root of 27 is 3. You can have answers that end up being the same number for 2 different roots because, remember, the roots are asking you for a different thing. What times itself 3 times gives me 27? What times itself 5 times gives me 32? So here's another one if you want to try this one real quick. The fourth root of 625, what times itself 4 times gives me 625, or what to the fourth power gives me 625? The answer would be 5. Now, technically, on an even root, you could also have a positive or negative 5. And when we start solving equations, we are going to have to remember that. Just like when we took square roots, when you have an even root, you do have to remember your plus or minus. With the odd roots, you don't actually have to remember it. Like I said, the good news is I'm not going to give you one as far as trying to find the imaginary numbers for a 4th root or a 6th root or an 8th root. You still need to know how to do it for square roots, but not for the higher even roots. So, here's a couple more for you to try. If you pause the video here and try them, then I'm going to go through them. So the square root of 1 here would be 1, or technically also negative 1. The cube root of negative 1, and this is where, again, you're going to have to kind of turn your brain off of imaginary numbers when you have an odd root. This is not imaginary. 3 times itself, negative 1, times itself 3 times, would give me negative 1. Or another way to think about it, like I said, is negative 1 to the third power would give me negative 1. The fourth root of negative 16, however, is an even root of a negative number. What you would answer for that, all you have to know is that there is no real answer or no real root to this. Because if this is an even root, it's going to be just like the square roots that we talked about. You can't have that. It'll be imaginary. Now, like I said, I'm not going to make you actually figure out the imaginary stuff for that. You still need to know how to do it for square roots. The 5th root of 243 is going to be 3. Now, you may be thinking, okay, Mr. Harrison, how do what if I don't know those? What if I don't have some of those memorized? Well, this is where a calculator can come in handy, okay? So you can take out a calculator like Desmos, and you can go in here and you can say, okay, 3 raised to the 5th power is 243, and that will help you figure that out. I do want you to understand that concept, but you can also, here's the neat thing, you can also use an actual root in the calculator, and this thing's going to mess up. Let me click on it with my mouse pad here, sorry. All right, so you can actually go into Desmos, and if you go over to this functions button, I think there might be another way to do this as well. Just forgive me. I'm just trying to go easy in this video. Underneath miscellaneous, underneath the functions, you'll see this little nth root that Mr. Harrison's talking about. When you click on it, it will let you put a fifth root into the calculator, and then you can type in 243 and it will tell you the answer. Just like we did earlier, if we go to that and we find the nth root or the cube root of 27 like we did earlier, we get 3. So when you are looking at this, you are finding the root using your knowledge or using the calculator to help you. The only thing I caution you on is that if you go straight to the calculator, you need to make sure that you understand what it's telling me, what it's asking me as well when I say the fifth root of something. So that way when you get to the calculator, if you accidentally type in something wrong, you'll realize it. You'll know that you got the wrong answer if it gives you something like 10 here. You're not dividing it by 5. Also, please be careful with that. It does look like division sometimes in people's heads. So be careful. You're not actually dividing it by 5. You're taking the fifth root. Make sure you can do that. The TI calculators. Oh, goodness. Sorry, guys. The TI calculators also have the ability to do this. I'll show you where they're at on here for those of you who like to use these. As I wait for the calculator to load here. Underneath this math button right here, if you click the math button, there is actually a little X root right here. Now, the tricky part on the TI calculators is you actually do have to hit the number. Like if I'm doing the fifth root, I hit the number 5. Then I go to the math menu, and I go down to this little number 5 here, hit it, and then it'll make that 5 into a fifth root for me. And then I can do the fifth root of 243. So when I'm looking at the calculators, yeah, the calculators are helpful, but don't forget what a root actually means. I'm okay with you using a calculator, but don't just overdo it. One of the reasons I tell you not to overdo it is because you also have to have the ability to simplify radicals like we did with square roots. We're going to show what that looks like here in just a second and practice it with some higher roots. But for a radical to be simplified, to be in simplest form, you have to make sure that you apply any properties of radicals, which we'll look at a little bit today. But you also have to remove any perfect powers, nth powers. Like if it's a cube root, you're looking to remove perfect cubes. Just like when we were doing square roots, we took out the perfect squares. You also have to rationalize any denominators. That is the one that's awful sometimes for people, but it is one that you have to be able to do. For variables, we'll talk about that in just a little bit. If we have time to get to that, I'm trying to keep this video relatively short. You know me and my talking, right? But for variables, we're going to look at that in just a minute, so I'll come back to that. If you're one of those people who likes to copy notes, you may want to hold off on the little variable part until we get to it if we have time. So, what I mean by simplifying a radical, let's go back to square roots back in the day. So the square root of 54, if you take out your calculator, I'm going to use this one because it's a little bit quicker. The square root of 54, you can use Desmos too, will give me a decimal. Now, please don't misunderstand me. It is very important that you know how to type in a square root into a calculator and get a decimal answer. And I'm not trying to offend anyone, but I could teach my son, who's 7 years old, I could teach him how to do this as well. I could teach him where the buttons are, how to push the buttons, how to type in numbers, and he could get this answer. So this is not a complicated thing to type in a square root in the calculator. What is complicated is when you have to simplify the radical, and you have to be able to do that, especially for imaginary numbers when it comes to square roots. So you want to be able to simplify this, not just type it in the calculator. This is called evaluating it if you find a value. So to simplify it, remember what we did was we took the square root of 54 and we split it up into 9 times 6. Now, what was the reason we chose 9 times 6? Was it because 9 is magical or 6 is magical? No, we chose 9 times 6 because 9 is the highest perfect square that divides into 54 because we're taking a square root. The square root of 9 would be 3, and then we leave the 6 inside the radical, and this is called simplified radical form. No, again, I understand. I get it. That's not easy. It's not the prettiest answer, but that's not what we're talking about when we say simplifying something. So when it gets to things that are cube roots or fourth roots or fifth roots, you do the same concept, but this time you got to be careful. You're not looking for perfect squares anymore. You're looking for perfect cubes. Yes, if you have some memorized, it'll be helpful, especially with cube roots. But you are looking for a perfect cube that divides into 54. Now, some of you are going to go, well, Mr. Harrison, how do I know what divides into 54? Well, if you can't do it in your head, use a calculator. You take your calculator out and you do 2 cubed, you're going to end up with 8. Oh, my goodness. This thing doesn't like me. I don't know why it does that little double tap. 2 cubed is 8. 3 cubed. Oh, man. Come on, guy. 3 cubed is 27. 4 cubed is 64. 5 cubed is 125. 6 cubed is 216. Guys, again, I had a teacher who told me I needed to memorize a few, so that's what I did. I memorized some. I didn't memorize a lot of cubes because you don't really need a ton of them, but it helps to have some perfect cubes in your head because then you don't have to go searching in the calculator all the time. Notice that 64 is already bigger than 54. So that means all I have to do now is say, okay, does 27 or does 8 divide into 64? Because 8 was a perfect cube, 27 was a perfect cube. 64 was a perfect cube, but 64 is too big. So I take out my calculator again now, and I go, okay, I'm going to see if those numbers divide into, wow, why is it doing that? 54. So I take 54 divided by 27. Notice I started with the higher one first. Press enter, it does. So 54 is 27 times 2. Again, 27 is not some kind of magical number. It's because it's a perfect cube, and I'm taking a cube root. Remember, we talked about 27 earlier. 3 cubed is 27. So the cube root of 27 would be 3. And then the cube root of 2 would still be inside the radical. So notice I take this thing that is a perfect cube and it undoes the cube and it comes out. So the big key to understand here is that when you take the root of something, it comes out of the radical and then you leave the stuff on the inside that's not. It's the same thing that we did with square roots. We took the square root of the perfect squares and we left the things that are not perfect squares on the inside. All right, so here's a couple for you to try. If you want to try them ahead of time, you can pause the video and try them. I'm going to go ahead and explain them, obviously, but you can try them if you want to. So 56 can be split up into 8 times 7. Again, why did I choose 8? Because 8 is the perfect cube that divides into 54. Wow, 56. Why am I doing 54? I'm looking at the screen again. Dumb. Sorry. You guys know me, right? 56 divided by 8. It's early in the morning. Sorry. 56 divided by 8 is 7. Because 8 is a perfect cube. Not because 7 is special. Not because 8 is special. But because 8 is a perfect cube. And I'm taking the cube root. So the cube root of 8 would be 2. And then the cube root of 7 stays on the inside. Now, some of you may be thinking, well, Mr. Harrison, you're doing that cube root of 8 too quick. How'd you get it? Well, guys, remember, I looked at it in the calculator. 2 cubed is 8. So the cube root of 8 would be 2. The answer to the cube root is staring at you if you use the calculator to find the perfect cubes. So we do the same thing with a fourth root. But now we're not looking for perfect cubes anymore. We're not looking for perfect squares. We're looking for perfect fourth powers. So again, I go to my calculator. 2 to the fourth power is 16. 3 to the fourth power is 81. 4 to the fourth power is 256. 5 to the fourth power is 625. Now notice 625 is already too big for this one. So when I'm looking at a perfect fourth power, they jump up pretty quick. And so you don't necessarily have to try a lot of them, and you don't necessarily have to have a lot of them memorized if you actually memorize them. So I know 625 is not going to divide into it, so maybe 256. But if I look at it, maybe I'm smart enough to tell 405 divided by 256, not going to divide evenly. Maybe I just try the next one down, 81. So you can take shortcuts if you know things that are not going to divide. 45 divided by 405, divided by 81 gives me 5. It divides evenly. That means 81 times 5, those are the factors of 405. Notice again, this whole factoring thing still comes into play, right? So the fourth root of 81, though, think about it back here. What gave me 81? 3 to the fourth power was 81. So the fourth root of 81 would be 3. And the fourth root of 5 would stay on the inside. And yes, Jeremy, there's a bunch of 3s. Jeremy's probably not even watching this video, is he? All right. So this is how you simplify radicals with the same techniques that we did with square roots. You also run into variables. I'm going to go ahead. I think I got plenty of time to do some variables here. You also run into variables from time to time. So I'm going to go back to the little notes page over here for variables. Notice what it says. It says for variables, divide the exponent on the variable by the index. The quotient will be the exponent for the variable outside the radical. The remainder will be the exponent for the variable inside the radical. So I'm going to show you what that looks like, but I'm going to show you why it works also, why this little shortcut here works. So what we do when we're dealing with variables is we say, okay, the cube root of 125, if you look that up or you do some math there, you'll figure out that it is 5. 5 times 5 times 5 is 125. But then for the variables, you just take this exponent on the variable and you divide it by the index. What is 6 divided by 3? Well, 6 divided by 3 is 2 with no remainder. So that means x squared will come out of the radical and there will be no remainder left in the radical. Now let's talk about why that works. So I'm just going to focus in on x to the 6th. X to the 6th really means x squared times x squared times x squared. That's one way of looking at it, and notice you multiplied it by itself 3 times. That's the cube root. The cube root of x to the 6th would be x squared times itself 3 times. Another way to think about it is this, using your properties of exponents from that other video you were supposed to watch. X squared to the 3rd power, because 2 times 3 would be 6. X squared to the 3rd power is what x to the 6th is. And when you take the cube root of a 3rd power, it cancels it out and leaves me with x squared. So all you have to do is just some basic division skills. So take a look at the next one. If you want to try it, you can pause it and try it. The 5th root of x to the 6th, y to the 13th. 6 divided by 5 is 1 with 1 left over, or 1 remainder. Another way to think about it is 5 goes into 6 one time with 1 left over. So that means you're going to bring out x to the 1st, and you're going to leave inside the radical x to the 1st, because there's 1 time with 1 left over. Guys, the reason is because if you take, and I'm going to use a different color here, x to the 6th, you can split it up into x to the 5th times x to the 1st. One of those is a perfect 5th. It comes out. And then the other one is not a perfect 5th. It stays in. So the tricky part a lot of times is realizing that when you do this, the exponent on the inside sometimes can be the same or bigger than the one you take out. Because when you take it out, you're actually taking the root. Just like when I take the square root of 9, I get 3 because it's a smaller number. 3 times 3 gives me 9. All right, so let's take a look at y to the 13th. 5 goes in the 13 2 times with 3 left over. So y squared is going to come out, because it goes into it 2 times, with 3 left over. Y to the third stays in. Now I know, again, this is not pretty, but this is how you simplify it. We're also going to talk about another way to write exponents and radicals next class. All right, take a look at the bottom one. The 5th root of 5. I bet some of you put 1 or said 1 just now, but be careful. 1 times itself 5 times is not 5. Be careful, don't start doing weird stuff. You're not dividing by 5. So the 5th root of 5 actually cannot come out of the radical because 5 is not a perfect 5th power. 2 to the 5th is 32. That's the lowest one you can take out. So 5, now with the variables here, 5 goes into 5 1 time with none left over. So a to the first comes out. 5 goes into 9 1 time with 4 left over. So b to the first, b to the fourth left over. 5 goes into 11 2 times with 1 left over. So c squared with c to the first left over. Again, I'm not going to beat you over the head with a ton of these on the test or anything, but I just want to make sure that you can understand how roots are working with numbers and with variables. All right, so we're going to do a couple more things, and then we will call it a lesson. So the things that we're going to look at are multiplying and dividing. So just like we did with square roots, like if you had the square root of 2 times the square root of 2, you would get the square root of 4, which is 2. Or another way to think about it, when you multiply square root times itself, you just get the number that's on the inside. That's another way to think about it. The square root of 8 times the square root of 3 is going to be the square root of 24. You can split that up into 4 times 6. The square root of 4 would be 2. And then you leave the 6 on the inside. Guys, I will point out here again, if you need a decimal answer, yes, you can just use a calculator to find that. But you can do the same thing with cube roots and with 4th roots and 5th roots, but they do have to be the same index to multiply them or divide them. We'll talk about later, there's some other workarounds for that using exponents. We'll talk about that next class. The cube root of 2 times the cube root of 4 is the cube root of 8. Well, what's the cube root of 8? The cube root of 8 would be 2. Then you can do the same thing even if it's got variables. The cube root of 3 x to the 4th y times the cube root of 18 x y to the 3rd. You're going to end up with the cube root here of 54. 3 times 18 is 54. X to the 4th times x to the 1st would be x to the 5th. Again, that comes from that other video you were supposed to watch. And then y to the 1st times y to the 3rd would be y to the 4th. The cube root tells me I can split up 54 into a perfect cube, which we did this one earlier, so I'm kind of saving us a little bit of time here. 27 times 2 is 54. Remember, the reason we choose 27 is not because it's special, but because it's a perfect cube. The cube root of 27 is 3, but I'll leave the 2 on the inside. X to the 5th here. 3 goes into 5 once with 2 left over. 3 goes into 4 for the y once with 2 left over. So the number of times that it goes into the variable's exponent, becomes the exponent for the variable on the outside, the quotient. The remainder is the exponent for the variable inside the radical. So that is multiplying radical expressions. And it can get ugly, but again, I'm not going to make them unnecessarily ugly. You just have to be able to work with these in a bunch of different ways. There's a lot of different types of radical things that you'll look at later in your mathematical careers, however long that may be. All right, so the last thing we're going to look at, probably the ugliest thing, is the 4th root of 16 divided by 80. Oh, crap. Division, right? The 4th root of 16 divided by the 4th root of 81 here. Notice if you have both of these in the fourth root, you can take the fourth root of each one of them separately, just like we did with square roots. We did this also with fourth roots and cube roots and all those. So be careful. Both of these are perfect squares, but that's not what I'm asking. I'm asking for the fourth root. When it's a nice, pretty little answer like this, you can actually just use the calculator to do this whole thing in the calculator and you'll be fine. Because the fourth root of 16, 2 to the fourth power, if you remember, is actually 16. 3 to the fourth power is 81. So the fourth root of 16 is 2. The fourth root of 81 is 3. When they're nice, perfect fourth powers like that, you can just use the calculator or you can use your brain to figure it out like I did. Now, be aware that you do have to be able to change answers back to fractions in the calculator if you need to. You can do that on Desmos or the TI calculators. Not going to review that right now at this point. Be aware that, yes, you can get decimal answers if you need decimal answers, if you need just approximate evaluations. But you also have to do something that we did back in the chapter with square roots. Back in the chapter with square roots, we realized, oh crap, sometimes the perfect squares are not there. Or like this one, it was the perfect fourth powers are not there. So if you don't have a perfect power, remember the big key thing is you have to be able to do what is the last little thing in simplifying, rationalize any denominators. Meaning, you have to make the bottom of the fraction be a perfect square. Or if it's a perfect fourth power, you have to make it be a perfect fourth power. So on the bottom of this one, we call this rationalizing the denominator because what we're going to do is make the bottom be a rational number. So we multiply by the square root of 2 on the top and on the bottom. We did this back in the chapter with quadratics. Again, we did this as a review when we were dealing with solving using square roots and using the quadratic formula and things like that. If you need to, I think there's actually a video still in the folder on solving using square roots where I do this. So if you need to go back. The square root of 2 times the square root of 2 is the square root of 4. But what is the square root of 4? That's 2. So what you did is you rationalized the denominator. You made it a rational number. It has some carryover into some other things that you'll do in your future as well. The square root of 3 times the square root of 2 gives me the square root of 6. So then I just leave the square root of 6 on the top. Remember, you can't divide something that's inside a radical with something that's out of a radical. They both have to be in a radical to be able to divide both of them. You do the same thing when you end up with something that is a fourth power, or fourth root, on the bottom. Except this time, we're going to try to make the bottom be a perfect fourth power. This is where you, again, if you know some fourth powers, it'll help you. 2 to the fourth power is 16. I can't multiply 9 and get 16. 3 to the fourth power is 81. I can multiply 9 to get 81. Now, I did this one on purpose because I want to make sure I point out something. This right here, where you have the same number here and the same number here, will not always happen when you deal with things that are not square roots. With square roots, yes, that's what you're trying to do. With fourth roots, you will not see that every time. Now, even with square roots, you can get to a few small examples that don't as well. But just, you've got to realize that I'm not getting 9 here because there's 9 here. I'm getting 9 here because I'm trying to make it be 81. Because 81 is a perfect fourth power. What is the fourth root of 81? Well, the fourth root of 81 is 3. So again, I didn't get 9 here because it's the same thing. I got it because I'm making it be a perfect power. On the top, 2 times the fourth root of 9 is all you can do. You can't really do anything with that except rewrite it. And 2 is not divisible by 3, so you can't reduce it any. This is called rationalizing the denominator. All right, let's look at this guy right here. One more example, we'll be done. I got one more thing to talk about, but I'll be done after that. So, if you want to try this one, it's got a little variable, got a little tricky part to it. Try to make the bottom be a perfect cube. That's the key. So hopefully, when you looked at this, you said, okay, I'm going to multiply it by a cube root because that's what we did with the fourth root. That's what we did with the square root. It's what we would do with any root. But I need to make it a perfect cube, not a perfect square, not a perfect fourth, a perfect cube because it's a cube root. So if you multiply by 4, 4 times 2 would be 8. But why did Mr. Harrison choose that? Well, because 2 cubed, oh, there it was. Sorry, I went the wrong way and I cleared it. Sorry about that. 2 cubed is equal to 8. It's a perfect cube. X squared is not a perfect cube either. 3 does not go into 2 evenly. So if I want that to be an even root to come out of the root on the bottom, what I would do here is I would multiply it by x. Why would I multiply it by x? Because then it would make it x cubed, which is a perfect cube. Sometimes if it's a bigger number right here, like if this was x to the 5th, you might have to multiply it to get it to be x to the 6th because 3 goes into 6. So what you're looking at there when it comes to a variable is you are looking at trying to make the x be raised to an exponent that will divide evenly by the index. And if you do too much, it'll fix itself in the long run. But typically what we try to do is we try to use the lowest amount that we possibly can. So the cube root of 8 is 2. The cube root of x cubed, 3 goes into 3 evenly one time, no remainder. Then on the top, I got 3 times the cube root of 4x, and I can't really do anything with that. And guys, again, I know it's not pretty. That's not what we're talking about when we talk about simplifying a radical. We are going through and using the radical, keeping it in that format, rationalize the denominator, taking out the perfect powers. That's the key. So you may want to go back and watch this video again, possibly over the weekend. The good news is Mr. Harrison is not going to give you any written homework over the weekend. That's my gift to you, if you want to call it that. What we are going to do with these roots also is not just simplifying them and dealing with radicals just for fun, but we're also going to use them to help us solve equations like these little guys here. When you have x to the 4th equals 625, instead of me having to factor it, I can solve it using a root. The bad thing is it doesn't always give you all the answers, especially when it comes to something like this. I can use a cube root to solve this right here, and it gives me x is equal to 2. Not plus or minus, because negative 2 wouldn't give me 8. Remember, odd roots only have one answer. But the problem is, we know x cubed should have 3 answers, right? Remember, this one would end up having some imaginary ones if you subtracted the 8 over and factored it. So it's not going to give you all the answers. This is the reason we don't learn this first. But it is going to give me the real answer, which is nice if I'm in a real-world situation with volume and I know I just need the real answers. This will help me out. All right. So I hope you guys have a great weekend. Again, please don't hesitate to watch this video a couple times if you need to. No written homework this weekend.